Hello again, Statistics 200 students. Welcome to Lecture 4 of this course. Today we're going to talk about histograms and graphs. So we're going to build on the information from Lecture 3 from our frequency distributions to expand to create histograms. But before we get started, let's show the joke of the day. Okay, moving on. We are still in lesson 2. We are still talking about summarizing and graphing data. Today, we're going to talk about histograms, and then we're going to look at graphs that convey useful information and graphs that actually deceive us. We'll start off talking about histograms. Okay. I guess no surprise here. We use a visual tool called a histogram to analyze the shape of the distribution of the data. Okay, so let's talk a little bit about histograms. Histograms are graphs consisting of bars of equal width drawn adjacent to each other. That's unless there are gaps in the data. So, pardon me, there will be a spot for a class that could just have 0 items in it. Okay, that's where the gaps of the data would come from. The horizontal scale represents the classes of quantitative data values, and the vertical scale represents the frequencies or the count of those data values. The heights of the bars correspond to the frequency values. Okay, that's the vertical scale. Okay, so last lecture we looked at the IQ scores from children with low levels of lead. Here is a histogram of that information. Remember, we generated, let me go back. We generated this frequency table last time, and from there we can generate this histogram. Well, it's nice that it's already shown graphed for you, but how did we get there? So I'm going to switch over to Excel here and show you how we can create this graph. Now remember, this is what we created last time. We have our frequency distribution table over here. Well, it's not letting me write in here. So here's our frequency distribution table. Remember, we divided these up to get our class widths. We then counted the number of children that fall into each category to get these values. Let me center this one. We computed the relative frequency by dividing this value by this value to get that. And then if we multiply this value by 100%, we get this. So that's the percentage frequency. This is what we did last time. All right, so how can we create the histogram here from this information here? Well, it's actually really simple. If you have this information, we'll just highlight the our classes here, and then our frequency counts here. We're going to go to Insert, and we're going to insert a chart. Okay, let's see if we can come up with what kind of charts do you think we want? Well, actually, that's it right there, the recommended chart that it gives us. But we're going to go to All Charts, and we'll look at a bar chart. Actually, we want a column chart. So a column chart that looks like that. Okay, we'll go ahead and, well, I mean, we could do color, but we'll go ahead and do this, and we'll accept it like that, and insert a histogram. Now, the result here is the frequency, yes, because that's what we have it labeled here as, but actually, it's the frequency or the number of children with IQ scores in the given range. And it's the number of children with actually low lead levels and IQ scores in the given range. All right, so there is the histogram. Oops, I don't want to do that. Pardon me. Now, this histogram looks a little different than the one here, but that's just because these are right next to each other, and these have a little bit of a gap. We can manipulate this to get them to where they are right next to each other just by changing some of the format, some of the design of our chart here. But we're not really worried about that as long as we understand how we get to this graph. Okay, so now moving on. A histogram is basically a graph of what? Well, what did we create last time? What did we spend the whole last lecture doing? We're creating a frequency distribution. So a histogram is a graph of a frequency distribution. We can use some form of technology to generate them. A calculator, if you have a graphing calculator, may be able to do it. Spreadsheet like Excel works really well. Some statistical programs, SAS, Jump, Statistica, there are all these programs out there that can generate them for you. But if you can produce the frequency distribution, then you can easily use Excel to create the histogram. All right. Now, the relative frequency histogram has the same shape and horizontal scale as the histogram. So if you look, this picture here looks identical to this one, except for this information right here. Has the same shape and horizontal scale as a histogram, but the vertical scale is marked with relative frequencies. So that's this here. These are percentages instead of counts. So this value here is that right there. This value here is right there. This value here is right there. Okay, so hopefully that makes sense. There's a lot of drawings on that slide now, but all that's happened here is that our y-axis, the scale, has changed to percentages instead of actual counts. Now, let's talk about interpreting histograms. Why do we use a histogram? Why do we generate them? Why do we waste our time creating them? So the object is not simply to just create one, but rather to understand something or to learn something about the data. So when graphed, a normal distribution has a bell shape. And not all histograms are bell shapes, but a normal distribution has a bell shape. Characteristics of the bell shape, we talked about this a little bit in last couple lectures. The frequencies increase to some maximum value and then decrease. There's symmetry, with the left half of the graph roughly a mirror image of the right half. And I drew one of these last time, and now I'm going to show you a graph how a bell would be overlaid over a histogram to kind of show, all right, well maybe this information is normally distributed. So what is the shape of this distribution? Yeah, it's roughly bell shaped or normally distributed. Where is its center? It's somewhere around 90, I would say. How much variation is in the data? Well, that's hard to say, but you can go from 50 to 150, or range of 101, or technically from 49.5 to 149.5, which is the same thing, because you have to include that, and that's, remember what we talked about last time. 150 minus 50 is 100, but you have to count 50 as 1 as well. That's why it's a range of 101. Now, are there any outliers? Well, it's possible that over here, that last one is an outlier because it kind of drags the tail over to the side a little bit. Because if you look, it makes the center over here, when if it was perfectly symmetric, it should be right there. So, all right, moving on. That was characteristics of the normal distribution. Now we're going to talk about a different distribution. This distribution is one for which the different possible values occur with exactly or approximately the same frequency. So the heights of the bars in our histogram are approximately the same. So we're looking at something, if this is a graph, where we have bars that are almost the same size, something like that. Okay, this is a uniform distribution. other types of distribution are skewed distributions. So a distribution is skewed if it is not symmetric and extends to one side, extends more to one side or to the other. Should be an or in there. Or if data is skewed to the right, then it's said to be positively skewed, and it has a longer right tail. Data skewed to the left is said to be negatively skewed, or negative skewed, and it has a longer left tail. So now, given all of that, let's look at some examples. So what would you say about this first one here, the green one? I would say it's roughly bell-shaped. So my drawing is horrible, but it's roughly bell-shaped. So what kind of distribution is that? Yes, it's normally distributed. The red one here, they are pretty much the same value all the way across. And if they're all the same value, then it's called, yes, correct, uniform or uniformly distributed. Now, if you look at this one in the bottom left, we have some kind of distribution here with a longer tail on the right side. So if it has a longer tail on the right side, what was it? It's right or positively skewed. And then this one, the brown one, has a longer tail on the left, so it's going to be the opposite. It's left or negatively skewed. Okay, hopefully you understand those. If there are any questions, feel free to email me. Now we're going to move into a different topic. We will cover this topic in much more detail in later lectures, and these are up in like the late teens or early 20 lectures. So you're looking at like 18, 19, 20, 21, something like that before we get into assessing normality. So don't worry about it right now. However, when we get into where we're actually analyzing data, a lot of the assumptions that we have for analyzing the data is going to require that the data must be from a population with a normal distribution. Okay, so we check whether it falls from a normal distribution using something called a normal quantile plot. So a normal quantile plot can be interpreted in the following criteria. If our normal quantile plot, if we graph it and it comes out that our points are reasonably close to a straight line, then we have a normal distribution. If, on the other hand, our points do not follow a straight line, or there's some kind of pattern, some kind of cyclical pattern, or some kind of pattern along it, then it's not a normal distribution. So this systemic or cyclical pattern is what I'm talking about there. So what does this mean? What am I talking about here? Okay. Oh, hey, part of the word got cut off here. This should say assessing normality, which graphs are normally, this over here should say distributed. All right, sorry about that. I guess there was a font change there. Okay, so the first one, we have a straight line through here, all right, and there's no, there's possibly a little bit of a pattern here, possibly something like that, but it's not a perfect pattern. So yeah, I'd say that's probably normally distributed, close to a straight line with no real pattern. Now, this one on the bottom left here, the data comes up and does this. Okay, the graph that would be produced from this when we do a normal quantile plot would be this green graph. And no, that's kind of the best fit of that information. So no, that doesn't resemble a straight line at all. So that information would not be normally distributed. And then the next one, this one is a little bit trickier because it looks like it follows a straight line. But if you look very carefully, you'll see that it actually follows this cyclical pattern. So because it follows that pattern, it is not considered to be normally distributed. Okay, so that wraps up histograms and a little bit of information about normal and normally distributed graphs. Now we're going to move into talking about graphs that enlighten and graphs that deceive. Okay, so what we're trying to do here is we're trying to find a graph that is suitable to display the information we have in a way that makes it easy to understand by our audience, whether it be, you know, some decision maker that we're talking to, whether we're trying to convince someone, you know, to make some decision. Well, it's best to be able to do that, or to use a proper picture, proper graph to convey the information to them. So some graphs are just bad in the sense that they have errors, and that's unfortunate, whether it be, you know, an oversight or whatever. But if you have errors in your graph, well, it's hard to recover from that. Some are bad because they are, while they're technically correct, they're misleading, and it's bad if you intentionally try to mislead. Sometimes you unintentionally mislead, and then hopefully someone catches this before it actually goes forward and is presented to anyone. Regardless, what we're trying to do here is to develop the ability to recognize bad graphs and identify exactly how they can be misleading. So we're going to go through a list of a bunch of graphs, and then I'm going to talk about some of those that are deceiving. So the first graph is a plot of paired data. We have XY data, XY quantitative data with a horizontal x-axis and a vertical y-axis. This type of graph is usually used to determine whether there's some kind of correlation, some kind of relationship between the two variables. And if you look, so this is waist circumference and arm circumference. Okay, so if you look at these two, as your waist circumference goes up, your arm circumference goes up as well. So that's saying that, you know, if you have a bigger waist, you probably have bigger arms too. So there's some kind of correlation there. And that's, I guess, probably not unexpected. This particular type of graph is called, a scatter plot or scatter diagram. So we have the XY graph is what this is. The next one we're going to talk about is data that have been collected at different points in time. So if you look, this is the yearly high values of the Dow Jones Industrial Average. This is the year on the x-axis, and the y-axis is the Dow Jones Industrial High. So this is time series data. Economists, people who do economics, econometrics, finance people use this kind of information a lot. The next kind of graph we're going to look at it's a graph that has each data value is plotted as a point or a dot along the scale of values. Okay, so dots representing equal values are stacked. So if you look, okay, let's take a step back. Let's remember what our data set looked like from last time. So here's our data set. Okay, all right. Let's go back. Okay, so there are 5 in this graph. There are 5 dots at 76. Okay, that's right here. 5 dots there. Why are there 5 dots at 76? Well, if we go to our data set, we have 1, 2, 3, 4, 5. 5 values of 76. There are 7 at 96. That's this peak right here. So we come back here, 96, we have 1, 2, 3, 4, 5, 6, and 1 more there. So that's why there's 7 there. And then we have, oh, sorry, wrong way. We have 1 at 141, which is way out here. And remember, we have this one guy here that we think may be an outlier. Well, this type of graph is called a dot plot, and it is pretty useful. Now, if you look at this and think for a minute with respect to our frequency distribution, our first class was from here to here, not including 70. The second class was from 70 to 89, not including 90. Then from 90 to 109, not including 110. From 110 to 129. And then from 130 to 149. Now, if you count the number of dots in here, it's going to correspond to the same values on our frequency distribution. This first one should be 2. This one should be 33. This is 35. Should be 7. 1, 2, 3, 4, 5, 6, 7. And this last one had 1. So we're portraying the same information. This is just another way to do it. Okay. All right, moving on. This next graph is called a stem plot or stem and leaf plot. Now what we, pardon me, what we do here, we're doing the same, portraying the same information that we did back up here. Okay, so we have 50 and we have 56. All right, so these first two here, we have 50 and then we have 56. So the way this is read, we have 5 and then a 0 and then a 6. Well, that means we have 50 and 56. So the 6 with no numbers after it means that there are no 6 values, no 60 values. So if you look, we go from 56 here to 70. Well, there are no 60s there. 7 here, we have 70, 72, 73, 74, 75. Remember, last time we said, hey, we've got 5 dots at 76. Well, here we have 7, and then 1, 2, 3, 4, 5, 6. Sorry, 1, 2, 3, 4, 5 sixes. So we have 76 5 times. Remember, we had 7 96s, so we've got 9. 1, 2, 3, 4, 5, 6, 7. 7 96s. Okay, so this is our stem plot, our stem and leaf plot. And then the next one we're talking about is one that uses bars of equal width to show frequencies. Well, that's a histogram or a bar graph. Okay, so our histogram that we did was a bar graph. And if you remember when we went into Excel to open that and portray it, we actually selected a bar graph. A graph that has 2 or more sets of bars and is used to compare 2 or more data sets is called a multiple bar graph. So this is an example of a multiple bar graph where you're looking at male and female median income in thousands of dollars going back to 1950 up to 2010. The next graph is called a Pareto chart. This is a bar graph for qualitative data. So if you look here, these are not values down here. They're categories, or there's some kind of divider that's not numerical. So a bar graph for qualitative data with the bars arranged in descending orders according to frequency. So they're always going to go down in value. All right. That's the Pareto chart. The next one, I'm sure no one can figure out what this is. A graph depicting qualitative data as slices of a circle in which the size of each slice is proportional to frequency count. Yeah, that's a pie chart. Yep. Okay, the next one is a frequency polygon. It's a line graph with the vertical axis representing the frequencies and the horizontal axis representing the class or the class midpoint. Recall that when we computed the class midpoint for our frequency distribution last time, well, this is a time when we can actually use that information. The next one is the relative frequency polygon. This one uses relative frequencies. So our proportions where we divided by the total number of, in our case, it was the total number of kids in the low lead level group. Well, here we have the high lead level group included as well. And so these are the percentages here. So that's this graph. The last one, the next one is actually called an ogive, a line graph that depicts cumulative frequencies. Yes, ogive is the way it's pronounced, not ogive or ogive, it's ogive. I had never heard of this graph before I actually started teaching this class. So I'm going to say that it's normally just called a cumulative frequency graph versus an ogive. But you can graph the cumulative frequencies, which we computed last time. Remember that we computed it using that table of cumulative frequencies. Now we're going to talk about some graphs that deceive. Graphs with a non-zero axis can be misleading because it tends to highlight differences that are not as big as they, or that appear to be bigger than they actually are. So here, if you look, highway fuel consumption, it looks like the Honda Civic is getting much better than the Chevy Aveo or the Toyota Camry. Well, that's because it starts at 30. So the difference between here and here is only 2 gallons, 2 miles per gallon, right? And the difference between here and here is 3. So when you actually go from a 0 scale, the difference is not that big. So if you look at this graph over here, the difference is not as pronounced as it is when you look over at the graph on the left. Pictographs are drawings of objects. So they can be 3-dimensional objects, money bags, stacks of coins, people. You can use this to depict these kind of information. Unfortunately, they can create false impressions that distort the data. And this has to do with how large an item gets, a 2-dimensional, 3-dimensional object gets versus 1 dimensions. And we'll look at that in just a minute. You'll understand why. Okay, so this first one here, we're looking at income and education. With no high school diploma all the way up to getting some advanced degree. So you got a bachelor's degree and then something higher. In this case, bars have the same width, but it's too busy, it's difficult to understand, and, is this, this relative to this is, I don't really follow this graph, okay? Well, this next one, all right, so if this is $18,000, going from here to here, that's only 4 times as much. But if you were to increase this length by 4, increase this length by 4, and increase this length by 4, you've actually increased it 4 times 4 times 4, which is 64 times. So the area within the cube has gone up by 64 times. So the last box is 64 times as large as the first box, but the income is actually only 4 times as large. So that's unintentionally deceiving, or it could be intentionally deceiving, but it's highlighting or portraying a larger difference than is actually there. Now here is just a bar graph, and you can easily see the scale here. Okay, that difference relative to this difference relative to this difference. So it's a decent graph. The only thing is that red is usually considered bad, and here we're going from kind of a pink opaque color up to red, with that kind of indicates that, oh, we're getting worse as we go up, which is not the case when you make more money. So I would say the only thing to do different about this graph is change it maybe from start blue and go up to green or something like that, just for human factors perspective. All right, let's look at an example where we're going to actually do it ourselves. Okay, so 40 office workers were asked how many cups of coffee that they drink in a day. And they gave their responses. And it's 0 all the way up to, it looks like 6 is the highest one. Man, that's a lot of coffee. I drink coffee, but not nearly that much. So here's what I want you to do. We're going to make a frequency distribution, a histogram, and a frequency polygon for this data set. It's actually going to be fairly easy, okay? How many, and then we want to answer the question, how many office workers drink at most 3 cups of coffee in a day? All right, so let's go ahead and do this. So first, let's determine the number of classes. I'm going to say let's use 7. We'll see why in just a minute. Calculate the class width, round up. Well, in this case, our data is tight enough that we can just use 1. So in this case, it doesn't make any sense to do, if we're going to do 7, that we would do more than 1 per class. All right, so starting point. Choose the minimum data value or convenient value below it as the first lower class limit. Well, our lowest value is 0, and we can't go any further below that because we're saying that someone drinks negative cups of coffee, which makes no sense. So the next step, use the first lower class limit and the class width to proceed to list the other lower class limits. Well, again, that doesn't make any sense to do it this way because our class width is 1. So our classes are just 0, 1, 2, 3, 4, 5, and 6. Same thing on step 5 there. So since we're only adding by 1, the upper and the lower class limits are the same. All right, step 6 here, count each individual data value in the appropriate class. The total is the frequency for that class. All right, that should all make sense. This is what we did last time. We're just kind of revisiting it, and then we're going to expand this to do a histogram. Putting the data set in order and separating them by their values will help. So here, I've done this for you. This is nice, okay. So here we have, this is just listing out the information. So here you can see we have 7 people who drink 0 cups of coffee. So we have 0 cups of coffee, 7 people drink that many. 3 people drink 1 cup of coffee. And then all the way out here, 15 people drank 2 cups of coffee. And then 9 people drank 3 cups of coffee. 3 people drank 4 cups of coffee. 2 people drank 5 cups of coffee. And then 1 person drank 6 cups of coffee and spent a lot of time going back and forth to the bathroom. All right. So there is our frequency distribution. Now I want us to create a histogram of this. Okay, so how can we do this by hand? Well, at this point, it should be fairly easy because we have our classes down here on the bottom, 0, 1, 2, 3, 4, 5, and 6. And we have our frequencies right here. So 0 has 7 workers that drank 0 cups of coffee. So how do we do that? We're just going to come right here in the middle to 7, draw that down. Okay, and if you want to shade it, you can shade it. Right, something like this. Okay. All right, so what's the next one? 3 workers drank 1 cup of coffee. So we'll come down here to 3, and they drank 1. Okay. 15 people drank 2 cups of coffee. So now we're all the way up here. Hopefully you can draw a straighter line than I can. And then we'll fill that in. Next we have 9 people drinking 3 cups of coffee. Of course, every one of these is an odd number. All right, 9 people drinking 3 cups of coffee. 3 people drinking 4 cups of coffee. All right, hey, there's our first even number, so I have another line to follow, and I did a horrible job with it. All right. 2 people drank 5 cups of coffee. So now we're down here. And then I remember we had that 1 person that drank 6 cups of coffee. So, putting it all nice and neat, this is what it looks like. Okay, but we actually graphed it out. Now, we want to construct a frequency polygon. Well, the nice thing about this is our class midpoint is the same as our class because our class width is the size of the class itself. The upper and lower boundaries are the same. So remember we had 7 people drinking 0 cups of coffee. What do we have? 3 people drinking 1 cup of coffee. Was it 15 that drank 2 cups of coffee? Yeah, 15 drinking 2 cups of coffee. 9 drinking 3 cups of coffee. 3, oh, that's not right. Oh, sorry, 3. I drew a 4 here. This should have been a 3. This should be 3. Yep, so if you didn't catch that when I did the error, I looked here and I said 4 people drank 4 cups of coffee. But actually it's 3 people drank 4 cups of coffee, so I graphed that wrong. So this, so the area right here should not be in there. Okay. So now we're at 3 people drinking 4 cups of coffee. So we're down here. 2 people drinking 5 cups of coffee over here, and then the 1 person that drank 6. So then we connect these dots. There, up to there, and it's supposed to be a straight line. Okay, so if you do it computer generated, it looks like this. And there's our frequency polygon. Now, how many office workers drink at most 3 cups of coffee a day? So at most, then down here. So 0, 1, 2, or 3. Well, it's probably easiest to look at it from our table here. So we have these people here. 7 plus 3 plus 15 plus 9. 7 plus 3 plus 15 plus 9. So this is 0 cups, this is 1 cup, this is 2 cups, and this is 3 cups. So how many is that? So 7 plus 3 is 10, plus 15 is 25, plus 9 is 34. So if you want to look at that nice and neat, that's what it looks like. Okay, so there's an example. We've shown graphs, we showed how to generate a histogram from a frequency distribution. We looked at different kinds of graphs, normally distributed, uniform distributed, different skews, and then we looked at all those other graphs, looked at examples, and then we worked an example. So hopefully you now understand all of that information with our histograms and then our graphs that enlighten and our graphs that deceive. Next time, we're going to go into methods to describe data, specifically measures of center, such as the mean, median, and mode, measures of variation, such as the standard deviation, the variance, and the range, and then measures of relative standing. Okay, we're also going to construct box plots to visually depict the data. All right, well, there you go. If you have any questions, feel free to email me. Thank you very much. Have a great day.